Okay, thank you so much. First of all, thanks for the invitation and for the introduction. And indeed, this work is joined with François and Hiroaki, the organizers of this session. So our goal with this work was to extend the Lagrange Dirac mechanics to account for systems whose configuration manifold is infinite dimensional, and more explicitly for systems in which we have a smooth manifold with boundary, so that the dynamics of the system is described through a system of PDEs as well as the appropriate boundary conditions. So we want a Lagrange Dirac setting in which these situations can be accounted naturally. So to begin with, let's recall briefly the finite dimensional case, which was introduced in these couple of works. Let me see. Okay. In this couple of works, the first one from the geometric point of view by using Dirac structures, and in the second one from the variational point of view. Here, we will only focus on the geometric point of view for brevity, but our results have also been obtained both from the geometric and the variational point of view. So, as any other geometric mechanical theories, we start from three ingredients: the configuration space, a smooth manifold, in this case is still finite dimensional, a distribution, which is the constraint distribution of the system, which can be possible non-integrable, so the system could be non-holonomic, and a Lagrangian defined on the tangent bundle of Q. And the main tool we use in Lagrange Dirac mechanics is the Talsio triple. The Talsio triple is a set of three maps between the iterated bundles of the configuration space, which has several properties. The first one is that they are canonical, so we don't need any additional structure on Q in order to define them. They are also global, so here I put the local expressions, but indeed they can be defined globally without coordinates. And they are also isomorphisms between those vector bundles, which are over the identity on Q, as you can see in the local expressions. And moreover, they are symplectomorphisms, as they respect the corresponding symplectic structures on the iterated bundles. So this set of three isomorphisms are the main tool to define the remaining objects of the Lagrange Dirac theory. Indeed, this omega flat is the flat map of the canonical symplectic form on T star Q, the cotangent bundle of Q. So how can we proceed? We define the induced Dirac structure on T star Q by using omega flat as well as the constraint distribution leave to the tangent bundle of the cotangent bundle of Q, and we define the Dirac differential of our Lagrangian by composing the exterior derivative of the Lagrangian with the map gamma. By doing so, we are ready to define the Lagrange Dirac equations for a vector field on T star Q. We couple this vector field with the Dirac differential, and we ask this pair to belong to the induced Dirac structure. When we compute the split expression, we obtain this locally, and in the case when there are no constraints, we obtain the implicit Euler-Lagrange equations. So, what happens in the infinite dimensional setting? Let's motivate this by an example. So consider a vibrating membrane with free boundary. So in this case, the membrane is given by a domain on R2, a closed and bounded domain on R2. Here I write Rm because for the computation doesn't matter the dimension in which we are working with. And the configuration space for this system is the family of smooth functions on B, on the domain. It is well known that the dynamics of this membrane is described by the wave equation, where phi is the corresponding function on B, the dots represent time derivatives, and nabla 2 represents the Laplacian on spatial coordinates, and tau and rho are just parameters of the system. And if we want our membrane to have free boundary, then the corresponding boundary condition is the Newman boundary condition, which says that the gradient of phi has to be tangent to the boundary at each point of the boundary, and here is the normal vector field on the boundary. Okay, this is a very well-known example, but however cannot be described with the previous Lagrange Dirac theory, as the configuration space is infinite dimensional. So let's see how can we deal with this example in the from the Lagrange Dirac point of view. So we start from the configuration space V in V. I denoted here by V instead of by Q because it's a vector space indeed. Is a Freche space, more particularly. And now, for the Lagrange Dirac formulation of mechanics, we need to deal with the cotangent bundle of V. since V is a vector space, the cotangent bundle is trivial, so it will be V times the dual of V. So now, since we have an infinite dimensional vector space, we have to take care about which dual we use. So first we have the topological dual, which is the more natural one, linear and continuous forms on V. However, this dual is too large, so we have to restrict ourselves to some subspace of the topological dual, which is smaller but large enough to account for all the properties of the system, and in particular for the boundary conditions. So we do so by using the restricted dual. So we define the restricted dual as, again, the family of smooth functions on V times the family of smooth functions on the boundary of V. This is good enough because we have two parts, the interior part, which will give the wave equations in the case of the vibrating membrane, and the boundary part, which will give the boundary conditions, and in the case of the membrane, the Newman boundary condition. To regard this space as a subspace of the topological dual, we need to define the dual pairing, and we do so by integrating in both the interior and the boundary of V. As you can see, elements of V star are pairs, a function on V and a function on partial V. That's why this makes sense. And this dual pairing is good because it defines a non-degenerate duality between V and V star. And thanks to this non-degeneracy, all of the steps that are performed in the infinite dimensional setting can be also mimicked here in the infinite dimensional setting. So we define the restricted cotangent bundle as V times V star, which, thanks to the previous lemma, is a vector subbundle of the topological cotangent bundle, V times V prime, and the same for the restricted iterated bundles, which will be needed for the Talsiu triple. In the last one, we need to define somehow V star star, but in the same fashion that the L2 dual pairing allows to see V star as a subspace of V prime, we can use the same pairing to regard V as a subspace of V prime of V star, the topological dual of the restricted dual of V. So we can define V star star just as V, and everything works properly. And we play the same game with the Pontryagin bundle. So we have the same spaces and the finite dimensional case, but with the restricted bundles. And now we can define the canonical one form on the restricted cotangent bundle of V, with the same expression as usual, but considering only restricted objects. So in particular, these angles there represent the L2 dual pairing on the restricted dual, with the restricted dual pairing, not in the whole cotangent bundle of V. By differentiating the canonical one form, we obtain the canonical symplectic form, and now we can consider the flat map of omega in order to define the Talsiu triple. However, at first, the flat map of omega will take values on T prime of T star V, but by making the explicit computations, one can see that indeed it takes values on T star of T star V with the definition in the previous slide. So everything works. And moreover, it fills the whole space, so it defines an isomorphisms, and we are ready to define the Talsiu triple. In this case, the expressions I write are not local, are global, since all of the bundles are trivial as V is a vector space. And by using this restricted Talsiu triple, we can define the remaining objects of the theory. We consider a Lagrangian defined through a density. This Lagrangian density can depend on phi, on the time derivative of phi dot, as well as the gradient of phi. The gradient is always taken in the spatial coordinates. And the Dirac structure, in this case, is given just by the graph of omega flat, since we don't have constraints in this case. So, in the same fashion, we define the Dirac differential by composing the derivative of L with gamma. Again, we have to take care, because since L is a map on TV, its derivative will live in T prime of TV, the topological cotangent bundle of the tangent bundle of V. However, since L is defined through a density, then it takes values on the restricted iterated bundle. So instead of taking values on T prime of TV, it takes values on T star of TV, which is a subbundle. So this is key. Our Lagrangian has to be defined through a density. And that's why we have chosen that definition of the restricted dual. Or in other words, how can we, from this point of view, motivate the definition of the restricted dual? Because the partial derivatives of a Lagrangian defined through a density naturally live on that space. That's why we have chosen to define V star as I showed you before. And now we have all of the objects, so the equations are just given by, for a curve, the derivative of the projection of the curve paired with the Dirac differential has to live in the induced Dirac structure. That's the same as in the infinite dimensional case. When we compute all of the computations, all of the explicit expressions of the objects, we arrive at the main result of this talk, the Lagrange Dirac equations for a system defined on the family of smooth functions on a closed domain on Rm. And as you can see, in the equations we naturally obtain the PDEs describing the evolution of the system in the interior of the domain, but also we obtain the boundary conditions. So yeah, our setting naturally accounts for both the behavior of the system in both the interior and the boundary of the system. For example, for the vibrating membrane, in which we obtain the wave equation and the Newman boundary conditions, we need to apply the previous equations to this specific Lagrangian. Now we have this, which is the main result. Let's see a couple of extensions of that. The first one would be very easy, and it's just including external forces. So if we consider a force with values on T star V, this force has two parts, the interior or distributed force as well as the boundary force. So the equations are the same, but with two additional terms, on the interior and the boundary, as expected. A non-trivial extension on this is considering K-forms. So now, instead of having a domain, we have a smooth manifold with boundary, a finite dimensional smooth manifold with boundary, and we consider a family of K-forms on that manifold. For K equals 0, we obtain a smooth function, so we recover the previous case. And in that case, we want to, again, define, it's again a vector space, so we want to define the appropriate restricted dual. And we do so by considering this space, n minus k forms on M times n minus k minus 1 forms on delta M, the boundary of M. Lowercase m is the dimension of the manifold. And the pairing here is given by integration, again, in both the interior and the boundary, but now we have to write the wedge product instead, to have forms of the corresponding order to be integrated. Again, the Lagrangian has to be defined through a density. The density taking values on the bundle of forms of M. So in this way, we don't have to fix a metric or a volume form in advance. And we consider the fiber derivatives of the Lagrangian as before. So we can repeat the same developments. We just reinterpret the fiber derivatives of the Lagrangian density by means of this map phi, but this is just technicality, it doesn't matter because we don't lose information with this map. And by computing the Lagrange Dirac equations for this case, we obtain the system of equations, where again the boundary conditions are naturally included in the equations. For example, we have applied these equations to electromagnetism, in which k equals 1, and we have obtained as expected the Maxwell's equations, and the boundary conditions are those of a system which is immersed in a perfect conductor, or from the mathematical point of view, this means that the magnetic field vanishes on the boundary of M, of the manifold. We have also extended this to forms with values on vector bundles, so we can account for non-abelian gauge theories, and for example Young-Mills theory, we have also done so, and in that case we obtain the Maxwell's equations as expected. Moreover, external forces can be added here as they can be added in the previous case. And for example, in electromagnetism or Young-Mills theory, they represent currents. So we can add external currents both in the interior or in the boundary of the domain in which our system is defined. In the case of K-forms, when k equals 0, both approaches are the same, but here we have an alternative definition for the restricted dual, which is given by these spaces of RS skew-symmetric tensor fields. Both approaches are equivalent, so one can use one of the other, but for the specific examples, maybe one approach is easier to compute than the other one. For example, for electromagnetism, this approach is more cumbersome and this other one is easier, but one can use the one is more useful in each case. So I think this is all. Some conclusions or future work. We are working on extending this to the nonlinear case, since all of the systems considered so far are vector spaces. So for example, if instead of considering forms, we consider diffeomorphisms on a smooth manifold with boundary, we can account for hydrodynamics in this case is easier because it's a Lie group, or a more complicated example would be continuum mechanics, in which one considers the family of embeddings of the smooth manifold M on a boundary list manifold. So we are working towards that direction, and also it would be interesting to consider the discrete counterpart of the theory in order to build variational or geometric integrators for the equations I show you. Okay, so thanks, and now any questions or comments you can ask.
So, is there any question or comment? Please?
Yes. Could you point the differences between the two systems you have obtained in your lecture? They are different?
Yeah, you mean this other approach, or?
No, there are two.
Okay.
This
Here.
one,
Yes.
and another one some slides before.
Okay,
what
yeah.
are the differences?
This is a particular
Yes,
case
yes.
because this is only valid when we are working in the family of smooth functions on the domain.
Yes.
And in the second system, we generalize the situation for the family of K-forms on any smooth manifold with boundary. So in this case, they are different because in this setting, one can fix the volume form because we are working on Rm. Well, I haven't written it here. Here, B is a domain on Rm, so we can have the Euclidean metric and that's it. And we fix the volume form, we call Bx. However, here in the extension to any smooth manifold, we don't want to fix any volume form a priori. So instead, we work with Lagrange density taking values here. So the expressions are a little bit different, but if one fix a Riemannian metric, for example, on M, and instead of working here, the volume form is fixed, then the equations would be pretty similar to the other ones. But that's the main difference. But those are an extension of the other one. You're welcome.
A nice formalism, but why do you use, you are working with the space of smooth fleets, while in functional analysis, people for rational problems, they use rather Sobolev-like spaces.
Yeah, so far we have worked with smooth functions because they are easier to deal with, and in the examples we have explored, those spaces are good enough. We don't need to consider more general spaces. But yeah, it could be interesting to see what happens if one considers Sobolev spaces instead.
Okay. So is there any comment or questions? I think we have some 2 minutes. Please.
I didn't really understand what the Dirac structure is, and can you explain this?
Yeah, sure. So in general, a Dirac structure on a vector bundle, here the vector bundle is T-star-V, but could be any vector bundle, is a distribution or a vector subbundle of the Pontryagin bundle of the corresponding vector bundle, which is isotropic with respect with a specific inner product, natural inner product that one can define on this direct sum of the vector bundle and the dual of the vector bundle. And for mechanics, one needs, for the Dirac formulation of mechanics, one needs to define a specific Dirac structure on this specific vector bundle, T of T star V plus T star of T star V. And we define this Dirac structure by using this graph, but of course we have to check that this is indeed a Dirac structure. We have done so. One can check that this object is maximally isotropic with respect to that inner product. I cannot write because there's not a blackboard here, but the inner product is easy because if you have two elements of something which is vector space times is dual, one can pair those elements naturally by the first covector paired with the vector and the second covector paired with the first vector. So this is a natural inner product of this direct sum, and that's how we define the Dirac structures. Thank you.
Okay, please.
If I remember it well, Dirac structure gives you a possibility to treat constraints in a quite efficient manner numerically. Does it also apply to this infinitesimal setting?
In this case, we haven't done it yet, but yeah, this setting is prepared to account for constraints. So maybe a possible generalization is considering constraints on our system.
Okay, okay. So now time is running out, so let's start speaking again.